It all begins with sand, not the golden beach kind, but a specific kind of silica sand, ultra-pure quartz, that gets refined into the glass that will eventually become the protective screen for the next-gen iPhone. Think about that for a second. The sleek slab in your hand once started life in a mine. That refinement process, those chemical reactions, those are the first steps in transforming raw earth into premium tech. From there, we move into the global supply chain, the nodes of sourcing, logistics, and manufacturing that underpin every model in the lineup. Next, the chip, the computer heart of the device, fabricated in advanced semiconductor clean rooms, often in Taiwan or Korea. The die is etched in nanometers, layered with transistors that number in the tens of billions. Once that wafer is sliced, packaged, tested, and shipped, it arrives at an assembly plant where thousands of precision machine tools and robotic arms await. It's here that the board is populated. RAM, flash storage, cameras, sensors, wireless modules, all placed with near-micron precision. The factory floor hums with conveyor belts, collaborative robots using vision systems, human workers performing joinery on flex cables and modules. It's a dance of man and machine, orchestrated to achieve both speed and zero defects. On the exterior, the chassis is made of aerospace-grade metal or ceramic glass composite, depending on the model. Milled, cleaned, anodized, coated, curved, each step adds to the premium feel. Meanwhile, the glass screen gets chemically strengthened through ion exchange processes. The surface atoms are swapped so that the glass becomes tougher, more scratch-resistant. Google this process and you'll find how even the early iPhones leverage this technology to stand apart. Night and day differences. Then there's the back glass, or finish, layers of paint, undercoating, laser etching logos, all handled in exquisitely clean, dust-controlled environments. A speck of dust can mean a reject. Waterproofing, dust-proofing, gaskets, seals, adhesives applied. Each port and each seam receives a pressure test. The device must survive spray, immersion, and still meet aesthetic standards. Internally, the battery is bonded and tested. The camera modules are aligned and calibrated. The lenses are inspected under multiple angles. The speakers tuned individually for frequency response. Wireless antennas positioned to minimize interference. This isn't mass production in the old sense. It's miniature precision manufacturing, optimized at scale. Then begin the lines of assembly. The main board is mated to the screen module. The chassis closes. Quality assurance stations check drop resistance, thermal performance, electromagnetic emissions. Software loads firmware. Sensors are calibrated. Cameras capture test images. A battery cycle runs. Each phone passes through dozens of gates before being boxed. You'll see workers affixing serial numbers, printing barcodes, and attaching packaging which itself has been designed to balance protection, sustainability, and branded experience. What's often overlooked is how much logistics matters in this system. Components must arrive just in time. Storage of parts is minimized to reduce obsolescence risk. The factory partners with air freight, shipping lines, customs brokers, and local governments. With recent shifts in global manufacturing, we're seeing factories not just in one country, but multiple assembly hubs moving from one region to another to avoid tariffs, supply bottlenecks, and geopolitical risk. Sustainability is also now part of the story. Recycling of rare earth magnets, cobalt from batteries, recovery of precious metals from failed units, all part of the life cycle. The factories include solvent-free paint booths, water recovery systems, solar arrays. When you hold a device, it's not just tech, it's the output of a global manufacturing ecosystem trying to balance innovation with responsibility. From the moment raw materials are mined to the moment the device is shipped out of the factory and lands in your hands, thousands of decisions have been made about design, materials, logistics, tooling, testing, assembly, packaging, shipping. Each one adds cost, risk, complexity. That's why the final product has its premium price, but also why so many users feel it's worth it. You're not just buying a phone, you're buying the culmination of global engineering, manufacturing, and supply chain mastery. Now think about you unboxing it. Every piece of packaging, the highlight color, the weight of the device, the subtle click when you insert a SIM, the first boot logo, those are user experience choices layered on top of technical choices. The factory delivered that experience, but the design studio envisioned it. From unseen tools inside the machine to the feel of that first swipe, the factory is the deliverer of promise. When you power it on, the operating system checks sensors, the chips coordinate camera functions, nodes. The network module looks for signal, the display adapts to ambient light. It's seamless because the manufacturing process paved the way for seamless. Precision placement of antennas minimizes dead zones. High tolerance ensures alignment. Thermal management within the enclosure ensures performance under load without overheating. Without hundreds of microengineering decisions aligning, your experience would degrade. Beyond what you see, what you don't see is just as important. Beta testing in factories, screening out units that fail reliability tests, performing environmental stress screenings, heat, cold, humidity, drop impact. These steps ensure that when you buy it, it works in your environment, whether you're using it in a humid city, a desert, or a snow-covered town. The factory and QA answer to that real-world expectation. And let's talk about volume and risk. Producing tens of millions of units within weeks of launch requires factories to ramp rapidly, train staff, calibrate machines, source parts. If one supplier fails, alternate routing or backup production must exist. That's why manufacturing planning begins years before the final reveal. The assembly lines are laid out months ahead, robotic cells qualified, operators trained, parts warehoused. When the one more thing launches on stage, that phone arriving in stores is the visible end of a near invisible global machine. Factor in costs, component shortages, currency swings, labor dynamics, transportation bottlenecks all pressurize margins. Factories can sneeze and the ripple reaches your wallet. That's why modern manufacturing strategies include inventory buffers, multi-sourcing, regional diversification. We're seeing that shift now with smartphone manufacturers who cannot rely on one country or one line to deliver the world's supply. Let's zoom back out and see how the factory concept itself has changed. It's no longer one giant factory in one place. It's a network. Some modules are made in Korea, shipped to India. Others in China, shipped to Europe. Final assembly might happen in one country, refurbishment in another, packaging in a third, and logistic hubs connect them all. For this latest flagship, the network has grown even more geographically distributed, multi-sourced, automated, and responsive. That's the only way to meet global demand. Tight launch windows and premium margins. From the end user perspective, what does this mean? It means the device you hold has passed through more hands, machines, audits, and test cycles than most electronics in your home. It means that every aspect, from the feel of the side button to the warmth of the finish to how the camera captures color, was likely fine-tuned at a factory floor somewhere or in front of a CAD console months ago. It means that the final product is as much a testament to manufacturing discipline as it is to design genius. Before you send your new phone on its first charge, imagine the journey. The sand carved out of the earth, the quartz refined, the chip etched, the screens polished, the cameras aligned, the antennas tuned, the board assembled, the chassis pressed, the factory humming, the quality gates spanning continents, the packaging filled, the supply chain humming, and then a plane crosses the sky delivering it to you. That story gives new meaning to designed in and assembled in. It reminds you that in a world of global tech, your device is the endpoint of thousands of kilometers of parts, people, machines, and decisions. But the real marvel isn't just the machines or materials, it's the coordination. In Apple's factories, every movement is measured down to milliseconds. Cameras monitor workers' actions to ensure perfect synchronization with robotic systems. Algorithms optimize conveyor speeds and even control ambient temperature so adhesives cure at precise rates. Every screw, every connector, every cable follows an invisible script written by years of refinement. Engineers in Cupertino design, test, and simulate assembly virtually before a single prototype hits the production line. By the time it does, the process is already a living, breathing choreography. Then comes automation intelligence, a hidden layer that most people never see. Apple's industrial engineers deploy AI systems that constantly analyze data from the factory floor. Pressure sensors, torque meters, and cameras feed thousands of data points per second into central servers. These systems can detect a 0.1 millimeter misalignment or a deviation in sound frequency when a screw is being driven incorrectly. That means potential defects are caught in real time, not after millions of devices ship. A major secret to Apple's success lies in its precision robotics. Specialized robotic arms equipped with haptic feedback insert components smaller than a grain of rice. Here, robots with sub-millimeter accuracy assemble the triple lens system, each lens positioned within microscopic tolerances to ensure focus calibration remains consistent across millions of units. These machines operate in clean rooms where the air is filtered 500 times per hour. Workers wear full-body suits, and even a single dust particle could force a production halt. The iPhone 17 marks another leap. Modular sustainability. Apple's suppliers have begun adopting recycled materials for structural parts, using reclaimed aluminum and rare earth magnets sourced from retired devices. Even the solder paste now includes recycled tin. Inside the assembly plants, waste heat from soldering machines is reused to maintain temperature stability in testing chambers. The result, the same cutting-edge technology, produced with significantly lower environmental impact, a step toward the company's ambitious carbon-neutral target. To eliminate bubbles, the process happens in a vacuum chamber. The resulting bond must withstand drops, flexing, and years of use. Then comes calibration. Robots align pixels with camera sensors and proximity detectors, ensuring touch sensitivity and Face ID accuracy remain flawless. Thousands of panels undergo burn-in tests before a single one is approved. In another corner of the facility, engineers focus on the battery assembly. It's not just about capacity, it's about energy density and safety. The lithium-ion cells are formed, aged, and rigorously tested under controlled humidity. Apple's safety teams simulate extreme conditions: overcharging, piercing, compression. Only after passing hundreds of safety checks are they installed into the aluminum housing using non-conductive adhesives and heat-resistant films. Every single battery is scanned, logged, and traceable down to the lot number of the materials used. The sound system, too, undergoes its own orchestra of testing. Microphones and speakers are subjected to acoustic scans inside anechoic chambers, perfectly silent rooms that allow engineers to analyze every frequency and distortion pattern. AI-based software then tunes the audio profile individually for each unit so that the sound output remains consistent even across different manufacturing plants. You might not realize it, but the crisp bass or clean treble you hear is the result of thousands of micro adjustments made during production. Let's not forget human craftsmanship. While the process is heavily automated, there are still key areas where human intuition prevails: visual inspection, finishing, tactile feedback. Workers trained for months learn to detect imperfections that machines can't perceive: the feel of a button click, the evenness of a brushed finish, the subtle glow of a display. Each worker signs off on batches that meet their section's standards, reinforcing the culture of accountability. To them, this isn't just assembly, it's craftsmanship at scale. Another layer of complexity lies in supply synchronization. Imagine thousands of components arriving from hundreds of suppliers across multiple continents, and each part must reach the exact production line at the exact time. If a single shipment is delayed, the entire operation can stall. After final assembly, devices enter the testing gauntlet. Each unit faces drop simulations, vibration checks, and waterproofing trials. Robotic fingers swipe across screens thousands of times to test durability. Cameras capture test images in calibrated lighting conditions. The phone's AI chip runs diagnostic programs, self-checking sensors, GPS, gyroscopes, and connectivity. Only if a device passes every test does it move to packaging. A single failure and it's flagged for rework or recycled immediately. Nothing leaves the factory unverified. Packaging, too, is a science. The iconic unboxing experience is engineered with precision. The soft friction as the lid slides off, the weight distribution, the minimalistic layout. Even the glue used for the box's edges is chosen for exact peel resistance. Workers use robotic arms to align packaging elements perfectly, and sensors check for label orientation and barcode readability. Every sealed box is scanned into the system, linked to its internal components by serial number, traceable all the way back to the raw material batch. Finally, the logistics symphony resumes. Pallets of sealed boxes are wrapped, loaded, and shipped via temperature-controlled freight. Some go by air to launch day markets, others by sea to distribution centers. Each carton carries embedded tracking chips, allowing Apple's global logistics hub to monitor shipments in real time. When you pre-order your phone and see "in transit," you're watching the culmination of this intricate ballet of precision, planning, and technology. If you found this breakdown fast, every Every day, people unlock their phones without thinking twice, but inside that sleek device is one of the most complex machines ever built. It all begins in a place buzzing with energy: Noida, India. Not just any city, this is where Samsung runs the biggest phone factory on the planet. Imagine walking into a space that spans over 129,000 square meters. That's more than 18 football fields laid side by side. The air hums with the synchronized rhythm of machines and humans working in harmony. This factory doesn't just make phones for India, it makes them for the world. Over 120 million of them every single year. Noida isn't just building devices, it's a symbol. It's where Make in India meets Make for the World. When the facility was inaugurated in 2018, India's Prime Minister himself flagged off the vision. Since then, this place has become the global brain of Samsung's mobile manufacturing, contributing nearly 25% of Samsung's global phone output. It all starts with a brain, and by brain, think of the motherboard. This isn't just a slab of silicon, it's a multi-layered marvel. It begins with a bare PCB, a blank canvas, but within seconds robots buzz to life, placing thousands of components, resistors, capacitors, chips with astonishing speed and pinpoint accuracy. Each SMT machine is a beast in itself, capable of placing over 3,000 tiny components in the time it takes to blink. The process feels like watching a futuristic ballet. Paste is applied with surgical precision, components are mounted, and then the board goes through a nitrogen oven. This massive furnace slowly bakes the layers, ensuring every component is fused just right. Then the board flips. The same steps repeat on the other side. Every tiny part has a job, and nothing goes to waste. The alignment needs to be so perfect that even a 1-degree deviation can break the entire circuit. These machines operate under strict temperature control, because even a small thermal shift could warp a connection. The paste used to attach components is carefully formulated to withstand heat and vibration. When the board exits the oven, it's inspected again, not by eyes, but by AI-powered cameras that never miss a detail. Optical systems scan for micro cracks invisible to the human eye. It's here that a decision is made, pass or fail, within milliseconds. Boards that don't pass are automatically routed to a diagnostic station where specialists determine the flaw. Meanwhile, flawless boards move forward, advancing like VIPs to the next stage. It's easy to forget that each of these boards is the beginning of a smartphone that might soon power someone's life. That board might end up in a school child's first phone, or a traveler's GPS, or a business owner's lifeline. Each one starts here, under the robotic arms and infrared lights designed to be tough but built with elegance. Even the sequence of the components, where each resistor, each capacitor is placed, is optimized to reduce power loss and increase efficiency. This isn't just about making phones fast, it's about making them better every time. What's wild is that every SMT line operates differently based on the phone model it's producing. One line might be working on a flagship, while another is assembling an entry-level device. The software driving each SMT machine is constantly updated, often remotely, by engineers monitoring performance trends in real time. This digital nervous system connects every corner of the factory, from ovens to optical scanners, from conveyors to cloud dashboards. It's smart manufacturing on a scale that's hard to imagine. Maintenance teams walk the floor, checking calibration, ensuring no nozzle is misaligned, no feed tray runs empty. At any moment, alerts can notify the floor team if a placement is even slightly off-center. Every machine has backup systems, every line has fail-safes. It's a fortress of accuracy. What happens in this SMT stage affects the entire life of the phone. A perfect board means fewer issues down the line, better battery life, better performance, and better user satisfaction. And because these machines are pushing limits daily, there's always a team of software and hardware engineers on standby, fine-tuning algorithms that guide these microscopic placements. The precision isn't just mechanical, it's emotional. There's pride built into every layer. Pride that this factory in India is setting the bar for global production. Here, Technology isn't just built, it's elevated, but it doesn't stop there. Inspection stations dot the production line using optical recognition and AI to catch the tiniest defects. These aren't just checks, they're safeguards. And after passing inspection, the motherboard transforms into a fully operational PCBA. It's ready for action. With the brain built, it's time to give the phone its face. The screen, sleek, fragile, and essential. To fuse the OLED and glass without a speck of dust getting in, the process takes place in vacuum chambers. Here, the environment is as sterile as a surgical room. Every bubble is eliminated. Every alignment is perfect. The slightest speck of dust can ruin the entire display. That's how delicate and demanding this phase is. And once the screen is ready, the next stage is where automation hits overdrive. Robotic arms place the screen onto the frame, sealing it in a way that no human could. The display isn't just slapped on. It's pressed at precise angles, especially for curved edges seen in flagship models. These tiny components are what allow screens to dim, calls to mute, and faces to unlock phones instantly. Each sensor is checked as soon as it's connected. Batteries slide into position next, sealed carefully, because safety is everything at this stage. No shortcuts, no assumptions. Throughout this process, phones keep moving, never stopping for long. Overhead screens track progress in real time, showing which unit is where and how long it's been there. If a delay happens, systems respond immediately. Another line compensates, another robot steps in. The rhythm never breaks. What stands out most here is balance. Humans and machines share the space without conflict. Robots handle repetition and precision. Humans bring judgment and adaptability. Together, they make sure every phone leaving this line feels exactly the way it should in someone's hand. By the end of this stage, the phone isn't just assembled, it's alive. The screen lights up, the system boots. A device that started as raw materials is now something ready to connect, capture, and communicate. And yet, even now, it's not done. The toughest challenges are still ahead, and the tests begin. There's the airtightness check. Not once, but multiple times. Instead of water, air pressure is used to simulate waterproofing. Fail the test, the unit gets pulled out, disassembled, and diagnosed. Only the flawless continue. But the real thrill, the drop test chamber, some call it the torture room. Robots drop phones from all angles, on concrete, on metal, on glass, up to 100 times. It's brutal, it's necessary. The goal: ensure that the screen doesn't shatter and the internals don't get knocked loose. And then function testing takes over. Robots simulate real-world use. Scrolling, tapping, typing, shooting videos, making calls. AI tracks power consumption, app performance, antenna signal strength, and more. There's even a special robot that doom scrolls TikTok all day long, testing battery drain under realistic scenarios. Nearby, rows of phones are tested in a fully automated microwave lab. These chambers test signal reception and transmission under conditions that mimic real-world usage, including body interference. Robots adjust phones to millimeter precision, ensuring every test is exact. Behind the scenes, data pours into terminals that engineers use to tweak future models. In another lab, engineers are testing materials, how glass reacts to UV rays, how hinges survive millions of folds, how polymers wear over time. Machines simulate years of use in hours. These stress tests are what make foldables durable and phones last longer. This level of precision ensures the phone works flawlessly under any condition. It's fascinating to see how every component has a role, no matter how small. Every stage of production is tuned like an orchestra, where machines and humans work in perfect harmony. Samsung's commitment to quality isn't just a slogan, it's built into every layer of the phone. From microscopic resistors to the glowing OLED screen, each part is a testament to engineering brilliance. The factory is alive not with chaos, but with rhythm, a carefully timed dance of technology. Robots aren't just assembling. They're thinking, learning, improving every cycle. In a single day, thousands of phones pass through these lines, each one a marvel of manufacturing. Behind every smartphone is a story of effort, innovation, and relentless testing. This isn't just production, it's perfection at scale. Every product is tracked, logged, and scanned dozens of times before it ever reaches a store shelf. This level of consistency is why phones from this facility are trusted by millions around the globe. All of this is supported by India's own research muscle. Samsung operates multiple R&D centers here, staffed by young engineers developing AI features that power the latest Galaxy devices. These teams contribute to everything from voice recognition to camera algorithms. It's not just manufacturing, it's innovation born and tested in India. And while Samsung's Galaxy AI-powered phones are assembled here, the factory doesn't stop at mobiles. Tablets and even premium AI appliances like refrigerators are also built under the same roof. It's a connected ecosystem built with precision and shipped across continents. This is the stage where all the hard work finally becomes visible. What once looked like scattered parts now starts to resemble something familiar. Frames glide in on conveyors, perfectly timed, never rushing, never waiting. The motherboard settles into place like it was always meant to be there. Cooling paste is applied in precise amounts, just enough to keep performance stable without wasting a drop. Every screw is tightened with calibrated force because too loose or too tight can change everything. Cameras are installed next, and this isn't just about plugging something in. Alignment here is critical. Even a fraction of a millimeter can affect focus, clarity, and image stabilization. Machines guide the placement, but humans supervise closely, watching for anything that feels off. Speakers are tested the moment they're seated, sending quick pulses of sound to confirm clarity and balance. If something doesn't sound right, the phone doesn't move forward, sensors are layered in quietly, almost invisibly. These tiny components are what allow screens to dim, calls to mute, and faces to unlock phones instantly. Each sensor is checked as soon as it's connected. Batteries slide into position next, sealed carefully, because safety is everything at this stage. No shortcuts, no assumptions. Throughout this process, phones keep moving, never stopping for long. Overhead screens track progress in real time, showing which unit is where and how long it's been there. If a delay happens, systems respond immediately, another line compensates, another robot steps in, the rhythm never breaks. What stands out most here is balance. Humans and machines share the space without conflict. Robots handle repetition and precision. Humans bring judgment and adaptability. Together, they make sure every phone leaving this line feels exactly the way it should in someone's hand. By the end of this stage, the phone isn't just assembled, it's alive. The screen lights up, the system boots. A device that started as raw materials is now something ready to connect, capture, and communicate. And yet, even now, it's not done. The toughest challenges are still ahead. The entire process is a showcase of synergy. Humans and machines, design and durability, software and hardware, all coming together to build devices that billions use every day. And after the testing and inspections are done, the final step begins. Packaging. The factory hums as many robots carry finished boxes, routing them to shipping lines. What started as a tiny PCB has now become a fully functional smartphone, ready to go global. The Noida factory isn't just big, it's smart, strategic, and a sign of how far India has come in tech manufacturing. With 120 million phones produced annually, this is more than a plant. It's a powerhouse. A symbol of vision, execution, and innovation. Imagine holding your MacBook right now. Sleek, slim, shiny. It didn't start life looking like that at all. What you're holding was once a chunky block of metal, and the journey it takes to become a MacBook is one of the most high-tech glow-ups in the world. Let's step inside Apple's factories and see how that transformation actually happens. When people think of Apple, they usually picture the polished end result, that sleek silver laptop resting on a cafe table, glowing logo catching the light like some kind of status badge. But the truth is, the real story begins much earlier, in a setting that feels less like a futuristic tech lab and more like an industrial warehouse stacked with raw materials. The MacBook's journey starts with aluminum. And not just any aluminum, this is high-grade, carefully chosen metal that has to strike the balance between strength, lightness, and style. Over the years, Apple has doubled down on using recycled aluminum, which means the slab that eventually becomes your MacBook might have once lived a very different life, as part of a soda can, a bicycle frame, or even an older MacBook that was returned and broken down for parts. Now picture those raw aluminum blocks rolling into the factory. They're chunky, plain, and about as glamorous as a brick. No sleek curves, no elegant ports, no delicate hinges. Just heavy rectangular slabs of dull metal. If you handed one to a stranger on the street and told them it was the first step to making a MacBook Air, they'd probably laugh. But that's where the real magic of Apple's process begins. Because in the next stage, machining transforms those lifeless blocks into something that starts to look unmistakably like a MacBook. The block heads straight into what looks like a lineup of robotic dentists armed with spinning drills. These are CNC machines, computer numerical control systems that can carve aluminum with ridiculous precision. Think of them as sculptors that never blink, never sneeze, and never lose focus, no matter how long they've been working. Each one attacks the slab from different angles, shaving off ribbons of shiny metal and slowly revealing the outline of a MacBook body. At first, it's barely noticeable, just a shallow hollow here, a slot there. But after multiple passes, the rough block begins to look less like raw material and more like the sleek frame we all recognize. The process is slow, deliberate, and oddly hypnotic to watch. You can almost imagine the machine sketching with drills, carving out the keyboard opening, the trackpad cutout, the vents for airflow, and the precise frame that will hold the logic board. Even the speaker holes are laser drilled so finely they look like they've been poked with a needle. Nothing is left to chance. Every curve and corner is executed with an exactness that borders on obsession. Because one misalignment here could mean a lid that won't close properly, a port that sits crooked, or a keyboard that rattles under your fingers. Apple simply doesn't allow that. Their engineers chase tolerances down to fractions of a millimeter, because that's what it takes to create that feeling of seamless perfection. And here's the surprisingly clever part. All that aluminum that gets shaved away doesn't just vanish into a trash bin. The curls, flakes, and powder are carefully collected and recycled right back into the system. Some of it might become part of another MacBook down the line, or maybe an iPhone case, or even something as simple as the internal structure of an accessory. It's a closed loop, a kind of aluminum circle of life. In a weird way, it's like a sourdough starter. You keep feeding it, keep reusing it, and it just keeps creating new things. Only in this case, instead of bread, it's fueling the creation of some of the most coveted laptops in the world. Once the outer shell is carved, the next stage is polishing and finishing. If you've ever wondered why a MacBook feels smoother than most other laptops, it's because the shells go through a spa treatment that would put most luxury cars to shame. Each piece is tumbled, brushed, and polished until it shines. Workers and machines check for imperfections because Apple's design language demands absolute uniformity. No weird edges, no tiny scratches. Just perfect silky aluminum. Now comes the coloring. Anodization gives the aluminum that iconic silver, space gray, or gold finish. This isn't just paint, it's an electrochemical process that alters the surface of the metal itself, making it tougher against scratches and corrosion. And because it's embedded in the material, the color doesn't chip off like regular paint. That's why your MacBook can survive years of coffee shop abuse and still look like it belongs in a museum of modern design. Meanwhile, in another part of the factory, the guts of the MacBook are being prepared. If the aluminum shell is the skeleton, then the logic board is the brain and nervous system. Tiny chips are placed onto the board with robotic precision. Processors, memory modules, storage chips, controllers. Apple's own silicon chips, like the M-series processors, are designed in-house but fabricated at specialized plants before being shipped to the assembly line. The logic board is small but densely packed. Every millimeter matters. Engineers plan out the placement so heat flows away properly, signals don't interfere, and everything fits into that impossibly thin body. Once the boards are tested and approved, they're ready to meet their shiny new shells. Assembly is where the orchestra begins. Imagine rows of partially built Macbooks moving down conveyor belts. Human workers handle some steps, placing the keyboard, attaching the trackpad, slotting in batteries, while robotic arms handle repetitive or delicate moves like tightening screws with exact torque. It's teamwork between man and machine. The keyboard deserves a moment of its own. It's not just a slab of plastic keys. Each key is engineered for travel distance, spring tension, and click feel. Apple has learned this the hard way. Remember the controversial butterfly keyboard? These days, every key is tested for consistency because the keyboard is one of the things users touch most. The trackpad gets similar attention. It's not actually clicking like you think. It uses haptics to simulate the feel of a click. That's why you can click anywhere on the surface, and it feels the same. Then there's the battery, one of the trickiest parts. Apple wants maximum capacity inside a slim frame, so the batteries are often custom-shaped to fit around other components. They're installed with strong adhesives to save space, which makes repair annoying. But from Apple's perspective, it's about efficiency and rigidity. Every battery is tested for charging safety, temperature stability, and durability. Nobody wants a MacBook that overheats or swells. Displays are another masterpiece. Each screen is tested for brightness, sharpness, and color accuracy before being attached. Apple calibrates them at the factory so you can open your MacBook and instantly get accurate colors, whether you're editing photos or binging Netflix. Cameras, microphones, speakers, they all get tested too. The speakers especially are tuned within the factory so they don't just play sound, they sound like a MacBook should, full, rich, and balanced despite the tiny space. Once all the parts are assembled into the shell, the MacBook still isn't ready to meet its future owner. Now it enters the phase that Apple is notorious for: quality control. Think of this as boot camp for laptops. They're powered on, connected, and put through a barrage of tests. Ports are checked to make sure they all work. Keyboards are typed on by robots that simulate years of typing in a few hours. Hinges are opened and closed thousands of times. Displays are flickered through test patterns. Fans are spun up to check cooling. It's relentless, but it's why you rarely hear about a MacBook failing straight out of the box. Some units go through burn-in testing, where they're run under stress for extended periods. If a capacitor fails, if a chip overheats, if a display flickers, those units are pulled and scrapped or reworked. It's ruthless but necessary. Imagine the PR disaster if thousands of MacBooks hit the shelves and died within a week. Apple avoids that with intense factory testing. After a MacBook survives all those trials, it gets cleaned, polished again, and then packaged. Apple's packaging is its own design marvel. Minimal, protective, and strangely satisfying to unbox. The boxes are made to stack neatly for shipping efficiency, and the internal trays are designed to cradle the MacBook without needing tons of plastic. Even the way the plastic wrap peels off is engineered for a wow moment. At this point, the MacBooks are ready to be shipped around the globe. Pallets of pristine boxes head to distribution centers, then to Apple stores, retailers, or directly to customers who clicked buy online. By the time you open yours at home, it's already survived one of the most tightly controlled manufacturing journeys in tech. Now let's zoom out for a second. All of this, the aluminum, the machining, the boards, the assembly lines, the packaging, it doesn't happen in one single building. It's spread across a network of factories, suppliers, and logistics hubs. Apple coordinates an insanely complex supply chain, pulling in components from different parts of the world. Screens might come from one place, chips from another, batteries from somewhere else, all converging at the assembly line. If one part of that chain hiccups, the whole system feels it. That's why Apple's factories are so secretive and so tightly managed. They don't just build laptops, they build predictability. Every machine, every worker, every supplier is part of a synchronized dance designed to churn out millions of MacBooks that are nearly indistinguishable from each other. If you buy a MacBook in New York and your friend buys one in Tokyo, they should feel identical. Same hinge resistance, same trackpad click, same keyboard feedback. That consistency is one of Apple's biggest flexes. What's wild is how much unseen detail goes into this process. Little things most people never even notice, yet they make a massive difference in the final product. Take the screws, for example. Those tiny fasteners holding your MacBook together aren't pulled off some random hardware store shelf. Apple designs them specifically for the MacBook, fine-tuning the size, the thread, even the shape of the head. Why? Because they want them to fit flawlessly, resist stripping, and yes, make it harder for just anyone to crack open the laptop with a basic screwdriver. It's part durability, part security, and part Apple being, well, Apple. The same obsessive thinking applies to glue and adhesives. These aren't just blobs of sticky stuff. They're carefully engineered compounds chosen for their weight, strength, and resilience under heat. They have to hold components tight inside a paper-thin frame without adding bulk or compromising longevity. It's the kind of decision that most users never consider, yet it plays a huge role in why a MacBook feels so seamless when you pick it up. Then there's the environmental side, which has become one of Apple's loudest talking points. But it's more than marketing. Every curl of aluminum shaved off during machining is swept up and recycled back into the system. Plastic in the packaging is minimized or replaced with paper alternatives. And even the inks used for printing on boxes are chosen with sustainability in mind. Hazardous materials like mercury or brominated flame retardants, once common in electronics, have been systematically reduced or eliminated. And beyond the good for the planet angle, there's a very real business logic here. If Apple can recycle its own aluminum, it reduces reliance on outside suppliers and fluctuating raw material prices. If its packaging is designed to ship more efficiently, lighter, smaller, easier to stack, that saves millions in logistics costs over time. So yes, it's about image and responsibility, but it's also about efficiency. In Apple's world, green is both eco-friendly and very profitable. So the next time you crack open your MacBook at a coffee shop, remember the journey it took from a raw block of aluminum to a precision-milled shell, from tiny chips to an integrated logic board, from stress testing to final packaging. It's a story of obsession, of design philosophy turned into manufacturing reality. Apple doesn't just build laptops, they choreograph an entire production ballet to make sure that what lands in your hands feels almost too perfect. And that's the world inside Apple's factories. A world where machines carve metal like artists. Humans fine-tune every detail. And the end result is the MacBook you know and love. If you enjoyed taking this tour with me, hit that like button. Drop a comment telling me which part surprised. It all begins with something most people never think twice about. A roll of metal. Not just any metal, aluminum foil, but not the kind you'd use in your kitchen. This foil is destined to become part of the powerful little device that sits quietly in backpacks, pockets, or desk drawers, waiting for the moment a phone hits 1%. This is the positive electrode in a lithium battery, the very heart of a power bank. Before anything takes shape, the aluminum foil is carefully coated. It's not just dipped in any liquid. This mixture is engineered to the molecule. It includes active materials like ternary compounds and lithium manganese oxide. Conductive agents help electrons move freely, binders hold the structure together, and solvents keep everything just the right consistency. The mixture is spread evenly across the aluminum using a precision coating machine, forming a sticky black film. Once coated, the foil goes through a drying process where all that solvent evaporates, leaving behind a perfectly smooth layer of electrode material. It's during this drying phase that the real transformation begins. The same coating process happens for the negative electrode too, except copper foil is used instead of aluminum. And that slight change in material makes a massive difference when it comes to battery chemistry. After drying, there's no time to waste. The coated electrodes are passed through a roll press. The goal here is to squeeze the material thinner and denser. That not only saves space, but ensures a consistent structure, which is crucial for performance. A properly pressed surface reflects light, almost like a mirror. That shiny finish? It's a sign the electrode is ready for the next phase. Now the material is trimmed, or what they call slitting. Picture these wide-coated sheets being sliced into narrow, clean strips, each one ready to be turned into the inner workings of a battery. The edges are flawless, the waste is vacuumed up and recycled. It's clean, efficient, and surprisingly satisfying to watch. Once the slitting is done, the next step is tabbing. Here, small metal tabs are welded onto both the positive and negative electrodes. aluminum tabs for the positive side, nickel tabs for the negative. These tabs will eventually be the connection points for the power bank's circuit board. But they're not just tacked on. Each weld has to meet specific tensile strength standards. If it's too weak, the battery won't survive assembly. If it's too strong, it risks damaging the thin electrode materials. It's all about balance. The machines performing these welds are tuned to microsecond precision, delivering just enough energy to create a bond without burning through the material. In a single shift, thousands of tab welds are performed, and each one must be flawless. Sensors monitor the current, pressure, and temperature in real time, flagging even the smallest anomaly. Sometimes a tab weld may appear perfect on the surface, but internal resistance tells another story. That's why additional electrical tests are often run after this step. Tabbing also sets the stage for how well the battery integrates into the larger power system. If the connection points are even slightly misaligned, it can cause serious issues during assembly. Operators often work under magnifiers, using cameras and screens to guide placement down to the millimeter. There's a visual rhythm to this stage, clean, consistent welds lined up like stitches on fabric. Each spark from the welder is a tiny burst of precision engineering. Depending on the battery format, the tab length and position might change, but the core principle remains the same: strength without compromise. Sometimes the tabs are folded or bent to prepare for the next stage, and that bend needs to be perfect. Too sharp and it could crack under stress. Too loose and it might not fit properly into the final pack. In high-capacity designs, dual tab configurations are sometimes used to distribute current more evenly. That adds another layer of complexity, but also improves performance. Engineers often revisit the tabbing stage when optimizing for efficiency or improving battery longevity. Even the tab material itself is carefully selected for conductivity, durability, and cost. It's a small part of the battery, but a vital one. In many ways, the tabs are the silent heroes of energy transfer. And once this precise dance of welding and alignment is done, the battery is finally ready to be shaped into the energy core that powers a modern device. With tabbing completed, it's time to build the core of the battery. Using an automatic winding machine, the positive and negative electrodes are carefully wound together with a separator sheet sandwiched in between. The separator does exactly what it sounds like. It keeps the two electrodes from touching each other directly. If they ever did, it could lead to a short circuit, or worse, a fire. Winding this way ensures compact, high-capacity cells that are safe and reliable. But winding isn't where the checks stop. The wound battery cores go through X-ray inspection. And yes, that means the inside is scanned like luggage at an airport. This step ensures the layers are perfectly aligned and free of defects. Any core that doesn't meet the standard is removed before it causes problems later. Once the internal structure is cleared, the battery core gets its outer layer. It's inserted into an aluminum plastic film casing. A heated copper mold seals the edges to keep everything airtight. This film isn't just for looks. It's flexible, strong, and lightweight, perfect for the slim, modern design expected in portable tech. But the battery isn't alive yet, not until it's baked, literally. These cells are placed in a high-temperature vacuum environment. The goal here is to remove every last trace of moisture from inside the cell. Even microscopic droplets can mess with performance or create long-term safety risks. After baking, it's finally time for one of the most important steps: electrolyte injection. The electrolyte is a special liquid that allows lithium ions to move between the electrodes. Too much or too little, and the battery won't work as intended. So every battery is weighed before and after the injection. It's not a guess, it's science. Only the correct amount will ensure proper function. The electrolyte acts like the bloodstream of the battery, enabling the essential chemical reactions that store and release energy. But it's also highly sensitive. The environment has to be perfectly controlled. Humidity levels, temperature, even air quality, all of it matters. During injection, the battery cell is placed in a sealed chamber to minimize exposure to air because the electrolyte can react negatively with moisture. It's why even a tiny air leak can ruin a cell. The machinery used for injection has to be incredibly precise. We're talking about fractions of a gram here, micro adjustments to ensure just the right balance. After the injection, each cell is immediately reweighed to confirm the added volume. If the weight's off by even a fraction, the cell is flagged for review. The process isn't rushed. The goal is saturation, not speed. Some manufacturers even allow a short rest period after injection, letting the liquid naturally soak into the internal layers. This helps reduce trapped air and ensures better contact with the electrodes. The chemistry inside is delicate, and even distribution is key. Uneven electrolyte levels can cause performance inconsistencies or premature failure. The liquid itself varies depending on battery type, but it usually includes lithium salts and organic solvents, engineered for fast ion mobility and stability. There's a whole science around optimizing this formula for different battery uses. High-drain applications need faster ion transport, while long-life batteries need better stability. The containers used to hold the electrolyte are often nitrogen-sealed to avoid contamination, and operators wear gloves, goggles, and full suits to handle it safely. Even a small spill can be hazardous. Once inside the cell, the electrolyte doesn't just sit there. It becomes part of the chemical symphony. It must fill every crevice between the tightly wound electrodes, acting as a medium that makes the battery come alive. This one step, so quick in real time, can determine how well a battery performs for months or even years. That's why it's treated with the same seriousness as a launch countdown. When done right, the cell is fully charged, not just with liquid, but with potential. Once the electrolyte is in, the battery enters its aging phase. No, it doesn't mean sitting on a shelf and collecting dust. It's placed in a controlled high-temperature environment to allow the electrolyte to fully soak into the internal materials. This step helps improve the long-term performance and stability of the battery. Next up is formation. This is when the battery is charged for the very first time, and that first charge is crucial. During formation, a stable SEI layer forms on the electrodes. This layer acts like a shield, protecting the battery from degradation while allowing ions to pass through during charging and discharging. Without this step, a battery wouldn't last very long. Before final assembly, there's a final gas extraction step using a vacuum. Any residual gases are pulled out of the cell to ensure nothing contaminates the battery over time. After that, the battery is trimmed, removing excess material around the edges. This ensures the battery is exactly the right size to fit into a power bank. But performance matters most. So each cell goes through capacity testing. They're charged and discharged to measure how much power they actually hold. Cells are grouped by their capacity levels to ensure consistent performance in the final product. If one cell performs worse than the others, it's removed. Only the best make it through. Next comes the OCV, or Open Circuit Voltage, test. This checks the self-discharge rate. Batteries are left untouched for a set period, and the voltage drop is measured. A healthy cell will hold its charge. If it doesn't, it's flagged and pulled from production. At this point, you'd think the hard part is over, but the real show is just about to start. Now it's time to assemble the power bank itself. Inside the Blue Times facility, these cells are lined up for a final round of checks. They go through visual inspections, voltage checks, and safety validations. Then 2 or more battery cells are paired together to form a single battery pack, increasing the overall capacity of the power bank. And this is where things really start to spark, literally. Spot welding connects the cells using nickel strips. These high-speed welds use intense heat and pressure to fuse the metal together. It's fast, loud, and dramatic, especially when sparks fly, but it's all controlled with incredible precision. These connections must handle both energy transfer and mechanical stress. Once the cells are connected, the brains are added. That means installing the protection circuit, also known as the BMS or Battery Management System. This tiny circuit ensures safety by monitoring temperature, voltage, and current flow. It's what keeps the power bank from overcharging, short-circuiting, or overheating. Without this, using a power bank would be a gamble. Now that the inside is complete, the casing comes next. This isn't just snapped together. An ultrasonic welding machine seals the plastic shell shut. Using high-frequency vibrations, it melts and fuses the case without using glue or screws. The result? A seamless finish that looks clean and feels durable. And once it's sealed, there's no going back. The case isn't meant to be opened. The power bank is almost ready, but it's not official until it's tested. The final device goes through more aging tests to simulate long-term use. It's charged, discharged, dropped, and shaken. And yes, there's even a drop test where the power bank is smashed against a hard surface to make sure it won't break or malfunction under real-world conditions. Only the strongest survive. For branding, there's a laser printing process that adds the final logo or product details. It's clean, fast, and permanent. And just like that, a brand new power bank rolls off the line. Sleek, compact, and ready to charge anything from phones to tablets and beyond. Behind every power bank is a journey of chemistry, engineering, precision, and innovation. And at the center of it all is Blue Times, a company with over 18 years of experience in building smart, sustainable, and reliable energy solutions. As a leading OEM and ODM partner, Blue Times doesn't just build power banks. They engineer trust, consistency, and performance. With patented designs, rapid development cycles, and factory-grade precision, their technology helps brands stand out while delivering the power users depend on every single day. From aluminum foil to circuit boards, from baking ovens to drop tests, this process is a reminder that portable energy isn't just about convenience. It's about innovation. It's about safety. And it's about turning science into something people carry in their pockets without ever thinking twice about it. And that's how power banks are made. Don't forget to like, comment, and subscribe for more behind-the-scenes looks into the world of tech, design, and innovation.